Okay, this is kind of that first lecture, chapter 1, kind of the throwaway, where we could just kind of talk about some of the basics. Okay, so again, what we're talking about in this course is engineering thermodynamics, and really what that is the study between the study of the relationship between heat and work. Okay, now as engineers, we look at a macroscopic or overall behavior. Okay, chemists, physicists sometimes look at a microscopic, how those molecules are bouncing around. It's called statistical thermodynamics, and we don't really care about that as engineers. We're looking at the overall outcome of how these interactions take place. Okay, so that's kind of the way we look at it. Now, a lot of what we talk about are systems, okay, and there's two main types of systems we look at in engineering thermodynamics. First is a closed system, where it's just that. It's the same amount of mass that's being processed in different ways. Okay, so it's all the same. The most common one we have is shown here. It's a piston cylinder, right, where you've got some fixed amount of fluid in there that's getting compressed and heated up and different things like that. Okay, but there's no change in mass during the within the system, as opposed to a control volume where we actually have like a fluid flow. So if we think of things like a compressor on an air conditioner, or on a refrigerator or something like that, right, where you've got fluid flowing through it, okay, and then that fluid is compressed or spins a wheel or does something like that. But the bottom line is that mass is actually crossing the boundary of our system, and mass is always intake and exhausted out. Okay, so mass can change. Now, there might always be the same amount of mass in there, but it's different mass as it moves through the system. So let's go through a few definitions. First is a property, and this is a characteristic of a system, right? So things like mass, pressure, temperature, these are what we call properties. It helps us define the system. It's something we can quantify within that system. A state is essentially a series of properties, or a collection of properties. So if I've got this pressure, this temperature, I'm at that state within the system. And in thermodynamics, as we'll learn, usually if we know two properties, we know all the other properties at that state. Okay? A process is basically going from one state to another state. In between those two states, we call that a process, and that's where, again, my properties are changing. Okay? In thermo, we're a little less concerned about the process and more concerned about the beginning and end states, before and after the process. Okay. Now, steady state, this happens when we have that control volume, right, where I've got mass flow. Okay. Again, properties may not change at the inlet or outlet. Again, mass is changing, or the actual matter is moving in and out, but the properties are not exactly changing with time. Okay, so that's what we call steady state. Equilibrium is a condition of balances where all the properties are uniform. So, that object that's been sitting in the room all day is the same temperature as the room. It's at equilibrium. It's not changing. Its properties are just hanging out, unchanging. Okay. Now, some units that we use. Okay, the base units we have. A lot of these you're going to be familiar with. The one you may not be familiar with is what we call the pound mass. Okay, so in thermo we just have a pound. Okay, now we might have a pound when we refer to mass. We might have a pound when I refer to as a force. Okay, as opposed to kilogram, newton. Maybe slugs and pounds. Okay, everything's a pound in thermo. I would encourage you not to think too hard about what I'm talking about when I talk about a pound. Just know that on Earth, which all of the thermo we're going to be talking about in this course takes place, 1 pound mass weighs 1 pound force. Okay, so a pound is a pound essentially. Now, depending on if we're talking about a mass or a force, it's different, but just recognize that in the general gravity sense here on Earth, 1 pound mass weighs 1 pound force. And if you don't think too hard about it, it shouldn't be too challenging to get through, although it is a different way to think, something you may not have heard of before. Okay, SI units are pretty standard. I'm going to assume most of you have seen those before. Okay, another main property that we look at is specific volume, which we're going to talk a little bit about the difference between specific, actual, that sort of thing, but really a specific volume is the reciprocal of density, right? mass per unit volume is density. Volume per unit mass is what we call specific volume, and many of the properties we talk about are in this mass form or this specific state. So we have specific volume. We'll talk more about things like specific energy and things like that moving forward. So the volume, the total volume, is what you're all familiar with. It's cubic meters, cubic foot. Okay. Now, for those of you who have taken chemistry, we have moles. Now, this is another one where don't think too hard about this stuff. We don't do things in moles and thermo. We deal with things in mass form because that's how engineers think. That's, we're going to weigh the thing anyway. We're going to figure out the mass, base everything on the mass. Okay. The difference between mass and moles is essentially the molecular weight of whatever substance we're looking at. For those of you that have taken chemistry, then you'll know that, for example, oxygen has a molecular weight of like 16. Okay? So to convert between the mass and the moles of an object is basically that factor, that molecular weight, capital M. And this can be found for many different substances in table A1. And we'll get to the tables much later on. But again, this is a common thing that we might need to do depending on, if we're dealing with water or air or carbon dioxide or whatever it is. Okay? So you can convert between moles and mass using that. Now, in the book, if you see a capital letter, like a capital V, okay, that just means volume that we're all used to. Okay? Lowercase v with a line over it is molar volume, so that would be that volume divided by the number of moles. I'm not even going to go too much into what a kilomole versus a pound mole is. Don't worry too much about it because, again, we as engineers always move to specific volume. Okay? So if for some reason you're given the molar volume, just divide, as shown here in that last column, just divide that molar volume, that little lowercase v with the line over, by the molecular weight to turn it into specific volume, which will always be lowercase v, which again is that volume per unit mass. Okay? So don't even worry, because I know you're all sitting there going, what's a pound mole? Don't even worry about it, right? The molecular weight is basically pounds per pound mole, kilograms per kilomole. Okay, you probably know it from chemistry is grams per mole. Okay, bottom line is we're instantly going to convert things, and the main thing to recognize is if you're given the molar volume, just divide it by capital M to get it into specific volume. So basically, anytime you see a variable with a line over the top, divide it by the molecular weight to get it without the line over the top. Get it in that specific terms per unit mass, which is the way we do things in engineering. Okay. Pressure, I'm going to guess a lot of you are familiar with. It's force divided by area, so that's a Pascal in SI units, right? Newton per square meter, or PSI, pounds per square foot. Now this is pounds force, not pounds mass, right? Because pressure is force over area, so it's pounds force per square inch. Okay. And 1 atmosphere is about 100,000 pascals, and we call that a bar, right? So 1 bar is 10 to the 5th pascals, and that's actually the unit we use most often. But just recognize that 1 bar is 10 to the 5th, kilopascals is 10 to the 3rd, megapascals is 10 to the 6th. But again, and then, the reason we use bars is because 1 bar is approximately 1 atmosphere, okay? Which is about 14.7 psi in pounds per square inch. Okay, so again, pressure is probably a concept a lot of you are familiar with. Temperature, I know you're familiar with, but it actually leads us to the 0th law of thermodynamics, which basically defines temperature as a property, which is one of the most important properties that we're going to look at. And that 0th law states that if 2 objects are in thermal equilibrium with a 3rd object, okay, then they are in thermal equilibrium with another. Okay, and this is really, what this means is, if they're in thermal equilibrium, all of the objects have the same temperature. That's basically what we mean by thermal equilibrium, right? If the temperature is not transferring, T is not transferring, there's no temperature change, it's in equilibrium. So this idea just defines temperature for us, okay? Units, again, most of these you're going to be familiar with. The one you may not be familiar with is the Rankine, right? These are absolute temperatures, right? So absolute 0. We deal with Kelvin, right, which is 273 degrees away from Celsius. Now, there's a English equivalent called Rankine, where 0 degrees Rankine equals 0 degrees Kelvin. But again, there's that 1.8 factor between the two, right? So 0 degrees Fahrenheit is actually 460 degrees Rankine. Okay, 0 degrees Kelvin equals 0 degrees Rankine, right? And you can convert between them. So again, the one that you're probably a little unfamiliar with is Rankine. So again, these are just kind of those general things that get us started. Okay, when we get into lecture 1, we'll actually get a little bit more, talk about actual thermodynamics.